Welcome to course on number theory. Number theory is one of the oldest and fascinating branch of mathematics. Almost all great mathematicians worked in number theory. For example, Pythagoreans, Euclid, Diophantine, Euler, Legendre, Lagrange, Gauss, Hardy, Srinivasa Ramanujan, Manjul Bhargava, Andrew Wiles, etc. This list continues. Many Indian mathematicians became world famous because of their contribution to number theory. For example, Acharya Jayadeva, Bhaskara, Brahmagupta worked on Pell's equation. Mahavir is the first Indian who gave puzzle using linear Diophantine equation. Recently in 2002, a computer science faculty from IIT Kanpur, Manindra Agarwal and his students Kyle and Saxena given a deterministic algorithm for primality testing. Because of that, they got worldwide recognition. Number theory is one of the interesting property. Here, problems are easy to state or understand, but it is very difficult to solve all the problems. For example, prime number theorem took almost 100 years to solve. It took approximately 350 years to solve Fermat's last equation. Still there are many open conjectures. For example, Goldbach conjecture, twin prime conjecture, Riemann hypothesis, this list also continues. With more than 2500 years of its history, number theory expanded tremendously. Now, number theory itself has many branches. For example, analytic number theory, algebraic number theory, topological number theory, computational number theory and so on. So, in one course it is difficult to cover a bit of it. So, in this course we just cover basics, that means one can say this is an elementary number theory course. So, there are many books on elementary number theory. For example, elementary number theory by Burton, elementary number theory by Jones and Jones, elementary number theory by Kenneth Rosen, elementary number theory and its applications by Thomas Cauchy. One can refer any of these books. This course divided into 5 chapters. Each chapter contains either 4 or 5 modules with the total 20 modules. In the first chapter, we will introduce different properties of integers, in particular divisibility properties. In the first module, we will discuss well-ordered principle and its applications and its equivalence to mathematical induction. Chapter 1 is fundamentals and divisibility of integers, and in module 1 we will discuss well-ordered principle and its equivalence to mathematical induction. Module 1, equivalence of mathematical induction and well-ordered principle. Objectives of this module are well-ordered principle and its applications, principle of mathematical induction and principle of complete or strong induction, well-ordered principle, principle of mathematical induction and principle of complete induction, equivalence of these 3. Before going to discuss those things, first we need to have some notations. The complex numbers, as every one of you will know, will be denoted as a plus ib, where a comma b belongs to R, where R is real numbers. So, as you know that if you look at this flow chart, complex numbers contains real numbers contains rational numbers contains integers contains natural numbers. And so, obviously what happens, any properties which are true for complex numbers automatically true for all their subsets. For example, multiplication satisfies commutative property in complex numbers. So, that property holds for all other number systems also. similarly associative property. But whereas certain properties which are true for subsets may not be true for the sets which contains them. For example, in the real numbers there is an ordering, but complex numbers we do not have any ordering. So, law of trichotomy is applicable for real numbers. Once it is applicable for real numbers, it also applicable for rational numbers, integers and natural numbers. So, but whereas law of trichotomy is not applicable for complex numbers. Similarly, if you take rational numbers, in the rational numbers we have the property that it is countable, but whereas real numbers are not countable. Similarly, in set of integers we have some nice properties that may not be true for rational numbers or real numbers or complex numbers. So, actually number theory is going to deal with we are going to study properties of integers, because in integers there is a symmetry, means 0, 1, 2, 3 and so on, minus 1 here. So, 1, 2, 3 and here minus 1, minus 2 and so sometimes we will confine to study its properties of natural numbers. Sometimes we will also study the whole numbers, that the whole numbers starts from 0, 1, 2, 3 and so on. Some others will take this whole numbers as natural numbers. So, first we start with well ordering principle. This well ordering principle is a property for natural numbers. In this module we are going to discuss properties which are hold for natural numbers, but not other systems. So, one such property is well ordering principle. Well ordering principle states that every non-empty subset of natural numbers has a least element. That is, it also stated as if S is any subset of n and S is non-empty, then S has a least element. By S has a least element we mean there is a S belongs to S and S less than or equal to T for all T belongs to S. Equivalent statements for well ordering principles are: first one, if S is contained in n implies either S equal to empty set or S has the smallest element. Other way to state is S is subset of n and S is non-empty, then S has the smallest element. Another way to state is S is subset of n and S does not have a smallest element, then S has to be empty set. For example, we will take S as set of all natural numbers, sum of whose digits is equal to 18. Then our objective is to find the smallest element in S. First we need to show that in order to use well ordering principle we have to show that S is a non-empty set. For example, if you see 5, 5, 5, 3, if you add the digits 5 plus 5 plus 5 plus 3, it is equal to 18. So, it belongs to S. So, S is a non-empty subset of n. So, by well ordering principle S has a least element. It is easy to verify that the least element of S is 99. Okay, another application of well ordering principle is prove that there is no positive integer between 0 and 1. Proof we will prove by contradiction. Suppose there is a positive integer between 0 and 1, that integer we will call it as A. So, that is blocked, it is written in the block letters. Let S is equal to n belongs to Z plus such that 0 less than n less than 1. Here Z plus means natural numbers. Since now S is non-empty because A belongs to S and 0 is A is less than 1. Therefore, by well ordering principle S has a least element, say L is less in between 0 and 1. In that case what happens, if you square L, that is L square is still less than L. So, we have an integer that is positive which is lies in between 0 and 1, but which contradicts the leastness of L. L is the least element. So, but we produce another element which is lesser than that, which is a contradiction. That is why there is no positive integer between 0 and 1. So, another example is prove that a non-empty subset of non-negative integers has a least element. This is just a generalization of result to natural numbers. This we prove by cases. In the previous example we saw we proved by contradiction, now we will prove by using cases. Let S be set of non-negative integers. First case we will take is if 0 belongs to S. If 0 is, since 0 is less than every positive integer, 0 is less than every non-zero element in S. So, 0 is the least element. If 0 does not belongs to S, then clearly S is a subset of natural numbers, that means S contains, may contain from 1 onwards. So, by well ordering principle S has the least element. Thus, in both the cases S contains the least element. Another interesting property or application of well ordering principle is Archimedean property. If A and B are two any positive integers, then there exists a positive integer n such that n A is greater than or equal to B. Assume the statement of the theorem is not true. So, for some A and B, n A is less than B for every positive integer n. Try to understand the negation of the statement. Here in the statement we are saying that A and B are any positive integers and there exists a positive integer n, but we are contradicting that statement. That means that there exists some integers A and B such that the statement n A greater than or equal to B is false, that means n A is less than B. Now, for it is for every positive integer. So, then we will consider the set, since we have to utilize well ordering principle. So, we will consider the set S is equal to B minus n A, where n belongs to Z plus positive integers. Then S clearly contains set of all positive integers, since because we are assuming n A is less than B. So, B minus n A is greater than 0. And further, by well ordering principle S has a smallest element, let us say that is B minus m A. So, look at the set S that is equal to B minus n A, n belongs to Z. Here the variable is n, A and B are fixed. So, the smallest element in S will be 1 that come by giving some value m to n. But if you consider B minus m plus 1 into A, that also belongs to S, but it is smaller than B minus m A, which is a contradiction, as B minus m A is the least element in S. So, now we will see, we will state principle of mathematical induction. Let us be subset of n that possesses two properties. The number 1 belongs to S. For every k belongs to n, if k belongs to S, then k plus 1 belongs to S. These are the hypotheses of the statement. Then we have S equal to n. This is what called principle of mathematical induction. You aware of this one. And another one is principle of complete induction. It is also called principle of strong induction. Here the statement goes like this. Let again S be a subset of n that possesses two properties. The number 1 belongs to S. If 1, 2, 3 and so on k belongs to S, then k plus 1 belongs to S. Then we have S equal to n. Why it is called strong? In the principle of mathematical induction, in the second case, in the hypothesis, we assumed that k belongs to S, then we have to show k plus 1 belongs to S, but here we are assuming 1, 2, 3 up to k all belongs to S. So, in order to show that the result the k plus 1 belongs to S, I can utilize any of those, means 1 belongs to S, 2 belongs to S and so on, k belongs to S. As we discussed well ordering principle and its applications, we saw several examples where well ordering principle is used. In this course, we will use well ordering principle very frequently, and we also introduced the statements of principle of mathematical induction and principle of strong induction. Now, we are going to see the equivalence of this well ordering principle, mathematical induction and principle of complete induction. These three statements, if you look at, they looks different, but they are all equivalent. One statement can be derived from the other. So, we will see these things. So, now we will the theorem is equivalence of these three, that is well-ordering principle is equivalent to principle of mathematical induction, which is also equivalent to principle of complete induction. We will prove in the following manner. In order to show these properties are equivalent, we show in this fashion. Principle of mathematical induction implies principle of complete induction. Principle of complete induction implies well-ordering principle. Well-ordering principle implies principle of mathematical induction. Now, with this each one is equivalent to each other. So, first we will prove principle of mathematical induction implies principle of complete induction. For that, what we have to do is we have to consider a set which is subset of natural number satisfying conditions of PCI, that means satisfying the hypothesis of PCI. We will show that S equal to n by using PMI. Since we are assuming PMI is true, we have to show PCI. So, we will show this result by using PMI. So, for that we will consider the set T. T is equal to n belongs to n such that 1, 2, 3 and so on n belongs to S. That means 1, 2, 3 up to n are in S. In that case only n belongs to n. If you observe this, the construction, one can easily understood that S T is a subset of S. So, once if we show that T is equal to n, then S automatically becomes n. So, we will show T equal to n by using principle of mathematical induction. So, now our objective is to show T is equal to n. To do so, we will use principle of mathematical induction to show that T satisfies hypothesis of PMI, hence T is equal to n. So, by definition, it is clear that T is subset of n. Our goal is to show 1 belongs to T. If k belongs to T, then k plus 1 belongs to T. Then by since we are assuming PMI is true, so T is equal to n. So, our objective is to show that 1 belongs to T. If k belongs to T, then k plus 1 belongs to T. So, first since 1 belongs to S, since S assuming principle of complete induction, so 1 belongs to T. So, we proved first part of the hypothesis of PMI. Now, if k belongs to T, then from the definition of T, we know that 1, 2, 3 and so on up to k belongs to S. Since S satisfies hypothesis of PCI, that we are assuming, so k plus 1 belongs to S. So, consequently what happens? 1, 2, 3 up to k plus 1 belongs to S. Hence, by definition of T, k plus 1 belongs to T. So, what we proved now? So, 1 belongs to T. If k belongs to T, then we showed that k plus 1 belongs to T. So, T is satisfying the hypothesis of PMI. So, by PMI T is equal to n. Let S is subset of n and suppose S has no least element. Then using PCI we have to show that S is equal to empty. It is because well-ordering principle says that if S is a non-empty set and S is subset of n, then S has to has a least element, but now we are assuming S is subset of n and S has no least element. So, we have to show that S equal to empty, that is equivalent condition of well-ordering principle. So, for that again we will define a new set T is equal to n minus S, that means we are removed S from n. Now, if you show that T is equal to n, then automatically S equal to empty. So, in order to show T is equal to n, we can utilize the properties of PCI. Means so we are proving by PCI implies WOP. So, if you are able to show that T satisfies the hypothesis of PCI, then we can use PCI and we can T becomes n, then automatically S becomes empty. So, our objective now is to show that T satisfies conditions of PCI. By definition, it is clear that T is contained in n. Now, our goal is to show 1 belongs to T, and if 1 comma 2 and so on up to k belongs to T, then k plus 1 also has to belongs to T. If these hypotheses if we show, then by PCI T is equal to n. So, we will prove one by one. clearly 1 belongs to T, otherwise what happens, 1 belongs to S. By definition T is equal to n minus S. So, whenever 1 does not belongs to T, then automatically 1 has to belongs to S. Then in that case 1 is the least element in S. So, but we are assuming that S has no least element. So, that is the reason. So, 1 has to belongs to T. Now, let assume that 1 2 up to k belongs to T, then obviously 1 2 up to k does not belongs to S. Again this is by definition of T. Now, we claim that k plus 1 does not belongs to S. What happens if k plus 1 belongs to S? If k plus 1 is in S, since 1 2 3 and so on 1 2 3 and so on k does not belongs to S. So, then k plus 1 becomes the least element in S. So, k plus 1 does not belongs to S. So, k plus 1 belongs to T. So, T satisfying the hypothesis of PCI now. That means 1 belongs to T, 1 2 3 and so on k belongs to T, then k plus 1 also belongs to T. Now, we are assumed PCI is true. So, T is equal to natural numbers n. So, or equivalently S equal to empty set. So, we proved PCI implies WOP. Now, we have to show that WOP implies PMI. So, we will assume that S is a subset of natural numbers satisfying conditions of PMI. Now, we have to show that S equal to n. So, in this case we will use WOP is true, since we are proving WOP implies PMI. So, again we will construct a set T as n minus S, as in the previous case we done. So, then we have to show that T equal to empty. So, once if you show T equal to empty, then automatically S becomes n. Suppose T is non-empty, then by well ordering principle T has a least element, say m. Note that m should be greater than 1, as 1 is already in S, that is because S satisfies the hypothesis of PMI. Also m minus 1 belongs to S, as m is the least element of T and T is defined as n minus S. So, applying the second property of PMI to S, we get m is equal to m minus 1 plus 1 that belongs to S, as m minus 1 is in S. So, m minus 1 plus 1 has to belongs to S, that means m belongs to S, which is a contradiction. It is because m belongs to T as well as in S, but that is a by definition T equal to n minus S. So, our assumption T is non-empty is false. So, S has to be equal to n. So, now we will see few applications of this principle of mathematical induction. The first example is, if C is not equal to 1, then 1 plus C plus C square and so on C power n is equal to 1 minus C power n plus 1 by 1 minus C. This is a famous example, every one of you know. So, proof goes like this. First we will take the base case, n is equal to 1, then LHS is equal to clearly 1 plus C, and RHS is 1 minus C square by 1 minus C. 1 minus C square can be written as 1 minus C into 1 plus C. So, we will get 1 plus C. So, base case is true, that is the result is true for n equal to 1. Now, induction case, here we will assume that the result is true for n equal to k. We will show the result is holds for n equal to k plus 1, that is we have 1 plus C plus up to C power k equal to 1 minus C power k plus 1 by 1 minus C, and we have to show for k plus 1. So, we will consider 1 plus C up to C power k plus 1. So, this is equal to 1 plus C plus up to C power k plus C power k plus 1. So, since the result is true for k, so 1 plus 1 minus C power 1 plus C plus up to C power k is equal to 1 minus C power k plus 1 by 1 minus C plus C power k plus 1. So, it turns out to be 1 minus C power k plus 2 by 1 minus C. So, hence by PMI the result is true for all n. Now, another example is this called Bernoulli's inequality. If x is greater than minus 1, then 1 plus x whole power n is greater than or equal to 1 plus n x for all n belongs to n. We will also prove by using induction. So, we will use PMI, principle of mathematical induction. Clearly, the result is true for n equal to 1 case. So, in if you substitute there 1 plus x whole power n greater than or equal to 1 plus n x, we will get equality, 1 plus x is equal to 1 plus x. So, the result is true for n equal to 1. Suppose the result is true for n equal to k. Now, we will consider n equal to k plus 1 case. So, consider 1 plus x whole power k plus 1, which is equal to 1 plus x whole power k into 1 plus x. So, clearly this is greater than or equal to 1 plus k x into 1 plus x, as x plus 1 is greater than 0. We are assuming x is greater than minus 1. So, that is why you will get this inequality. Consequently, we have 1 plus x whole power k plus 1 is greater than or equal to 1 plus k plus 1 into x plus k x square, as we are using now induction here. So, greater than or equal to 1 plus k plus 1 into x, as k x square, since k is a natural number, x square is also positive. So, k x square is positive. So, clearly 1 plus k plus 1 into x plus k x square is greater than or equal to 1 plus k plus 1 into x. So, hence the result is follows from PMI. In this module, we discussed properties of Aladdin principle and its applications, and we saw its equivalence to principle of mathematical induction and principle of complete induction. With this module is completed. So, we will see other properties of integers in the next module.